So we're going to be talking about results from our latest paper. I'll spend about half the presentation giving a refresher on human preference learning and why we care about this. And then the latter half, I'll talk about our results and our method. So first, I'll just do a quick introduction. So I'm Daniel Fein. I'm a master's student at Stanford, where I'm advised by Max. Max, you want to give a quick intro?
Hi everyone, I'm Max. I'm a research fellow here at Stanford. I work with the Stanford Intelligence Systems Laboratory and the Stanford Center for Air Safety and the Hoover Institution. And it was a pleasure working with Daniel on this project.
Great. So I'll start this off by asking everyone which of these two images you prefer. So maybe if you prefer the image on the right, you can press raise hand. Okay, great. So there is at least some preference for the image on the right. So the purpose of this demonstration is to basically say capturing human preference is pretty hard. So think about this, like different people have different preferences. So there's like diversity. And also there's a lot of complexity that goes into like which one you actually prefer, whether you're thinking about the flavor, whether you're thinking about, oh, I interpreted this question as referring to the pictures. So measuring human preferences is something that's actually harder than it might seem. And why do we care about measuring human preferences? So we're at a point now with progress in language models where we're very good at achieving high superhuman performance even in any task that we can actually measure. And this plot is often shown to point to the fact that we're now more quickly able to achieve progress on any task that we begin to measure. But I think a often like overlooked element of this is the fact that actually we always start at zero. So despite having like these general language models that do just in general get better as we train on more tasks, we also are not really able to perform well at tasks until we can measure them. So for that reason, measuring human preferences is really important. And in fact, what I just showed you is basically our best method for doing exactly that. So on the left, we have Ella Marina, but this is also how, in general, human preferences are, how language models are aligned to human preferences. And just like in the ice cream situation where, there were a lot of competing factors for our attention in terms of which one we selected, if you look at the image on the left, basically, you can think of a lot of reasons why you might select assistant A versus assistant B, whether it's the formatting or you prefer the bold text or like the way that the information is presented. So measuring human preferences is difficult, and that's kind of like the purpose of this paper and what we'll talk about more now. So our ultimate goal is to train a helpful and harmless language model. This is also like alignment as the goal, but just zooming out. I'm going to start with a quick like trivia question, which is, what's the difference between statistics and machine learning? If anyone has like a good idea, feel free to drop it in the chat. Oh, also, I just realized Max has his hand up. Is there something you want to add, Max?
Oh no, I'm sorry, that was for the earlier voting thing. I just didn't put it down.
No worries.
My bad.
No worries. Okay, so actually we got one correct answer in the chat, which is that the difference between statistics and machine learning is generalization. So if we have a data set and we're trying to just understand it, that more so falls into this field of statistics. But the thing that separates machine learning is that we actually have a distribution of data that we're allowed to see and a held out distribution of real data that we don't get to see. So I'm going to use these two circles kind of throughout the talk to represent our training data that we actually get to see and our real data, which is like the problem that we want to address in deployment. So for like the problem of alignment, you can think of how this gap might be big. Real data is like anything that anyone wants to talk to any language model about, and training data is whatever we're able to come up with to train the models to be how we want them to be. So a quick case study is next token prediction. So next token prediction is like the ideal machine learning task where we have lots of training data, like any text that you could possibly imagine can be turned into this task of next token prediction, and it's often called self-supervision. And the other thing, which I'm going to introduce this term from a paper earlier this year, is that the task is high epiplexity. So someone invented this basically saying that from information theory, we have the idea of entropy, which is like, how much surprise is contained in the data set. But that doesn't really indicate how learnable a task is. Instead, there's like this other quantity, which they call epiplexity, which is meant to describe how much underlying structure there is within the task. So for next token prediction, it's this very difficult task. There's all these possible next tokens at each point, yet there's a lot of consistent structure that underlies it, such that the task is actually learnable. Okay, so how might we think about, like in this framework, training this helpful and harmless language model? So we immediately encounter two big problems here. The first problem is that human data is really expensive. So it's not like next token prediction where we can turn anything into preference data. And even researchers have had difficulty turning long chat conversations that users have into preference data. It's often unclear whether the person is actually like enjoying or having a good experience talking to the model just from how they interact. Instead, we need to rely on that task of giving people preferences. And not only that, because you saw the complexity with the ice cream example, we actually need to make sure that these people are focused and really like have the best interest of making the model as good as possible, which is often not the case, as I'll talk about more in the future. The second problem is that our data doesn't necessarily capture exactly what we want it to. So this is, again, going back to the ice cream example, there's a lot of other factors, depending on the context with which you approach this ice cream question, that might determine whether or not you prefer the right or the left image. So in this example, for example, I asked you to raise your hand if you prefer the image on the right. And this is a presentation and you might not want me to be up here and have no one raise their hands. So that might also drive you to raise your hand. There might be other factors other than your actual preference that drive this decision. So this is our final pictures. We have this training data that's kind of off center and small of like the actual space of what our in deployment models are going to encounter. Okay, so how do we address problem one? And some people might sort of take issue with this likening reinforcement learning to synthetic data, but I think it's often the case in preference learning, at least, that this is what reinforcement learning amounts to. So the basic idea is, because we're not going to be able to train our model on all of the sort of prompts that it would actually encounter in the wild. Instead, we're going to try to use the generalization abilities of a separate model, which we're going to call the reward model. And we're going to train the reward model on our human preferences that we've collected, even if we only have, say, 100,000 of them. And we're then going to use the reward model that's trained on our data, and that's what's going to teach the language model. So basically, the language model will generate text in response to some prompt, and it'll generate, say, 8 variants for a given prompt. And then the reward model will, based on its understanding from the training data, give a score to each of these responses from the language model, which will then be used to inform the language model which of its responses were best and try to steer it towards giving good responses as determined by our reward model, which is trained by our data. Okay, so how does this solve the problem of not having enough data? Well, if you only have 100,000 examples of good behavior, but then you have a reward model that can capture some more underlying idea of a good answer, then in this training loop, we can actually create the data that's totally unrelated to our training data, but which the reward model hopefully still has some good idea of how to handle. So how do we actually train a reward model? There's something called the Bradley-Terry model, which is actually an old idea, but it's repurposed for this. And basically, we take this preference data, which is this like right-left comparison. How do I fix my door? For example, could be a prompt. And we have a label that's leave it broken is a bad answer. And you can begin by checking that the hinges are aligned is a good answer. So the reward model might give this top one a bad score. And this is literally a scalar score. And it might give this, you can begin by checking the hinges are aligned, a slightly better score. So then our Bradley-Terry loss function tells this reward model, okay, this one was labeled as bad, so we're going to try to reward less for that in the future. And this one was labeled good, so we're going to reward more. And this arrows represent backpropagation. Okay, the issue with this is that our off-center data problem, our problem where our collected data doesn't exactly match our training distribution, has actually become more of a problem. Because if we're scaling up the amount of training data using this reward model, which is like trained on our training data, then we're actually scaling it up potentially in directions that are not overlapping with our real data. So more concretely, basically, our reward model, if it has imperfections, our model can actually figure out how to get a good reward without actually learning how to do the task correctly, but instead by cheating and taking advantage of how our reward model might be flawed. So here's an example of this to make it really concrete. If you remember, I think like GPT 4.0 or one of those early models really liked emojis. Even the first version of ChatGPT really liked emojis. And I think it's probably because in that training data, the preference data collected, people tended to think it was cute or funny when the model used emojis. So then our reward model basically has this idea that people like emojis, and that when more emojis are present, I should give a higher reward. And then what happens is that during reinforcement learning, this becomes reinforced because our agent, which in this case is our language model, will think, okay, what if I try adding an emoji? In its random sampling of 8 responses, it'll add an emoji. And then the reward model will say, oh, people really like that. And that'll become reinforced in this feedback loop, because the reward model might not necessarily have an idea, okay, well, maybe people shouldn't always write emojis because maybe the training data only includes a small 100,000 examples. So this agent would learn that emojis are good and more emojis are good regardless of whether the substance of the message actually responds to the user's query. So this is what we call reward hacking. So one family of causes that can contribute to reward hacking, and this is the one that the emoji example fits into, is called reward misgeneralization. So what this means is that we have a reward model, and the language model, our agent, it's also called our policy, learns to sort of abuse and cheat one of the aspects of the reward that's correlated, one of the aspects of the output that's correlated with reward in our reward model. So really common examples of this, the emoji one, of course, but also length has been really focused on, because this is a plot of reward versus output length for a couple earlier popular reward models. And we see that there's like a very strong correlation between length and reward. So basically all of these models for a very long period of time would just learn to write a lot of text in response to almost any query, just because if you wrote more text, regardless of what it was, you got a higher reward. Okay, so now I'm going to shift a little bit to talking about our method in our paper, which is called One Bias After Another. And we introduced this word called mechanistic reward shaping. And I'm going to explain what this is. Another thing to note here is my question here is, can we clean these spurious correlations out of trained reward models by operating on their activations? So spurious correlations are often, is the word we often use to describe the issues with reward models that lead to reward hacking, because they're spurious to the actual goal of human preference learning while being correlated with our reward. Okay, so now I'm going to talk a little bit about the actual structure of our reward model so we can understand this method. So how do we make a reward model? I talked a little bit about this before, but now we're going to zoom in a little bit and talk about the actual structure of the reward model. So reward models are commonly just language models where we lob off the end the part that actually predicts words, like the next token, and we replace it with this reward model head. So for a quick refresher, the language model basically takes each token and breaks them into takes the sentence and breaks it into tokens which have corresponding embeddings, and then alternates through attention and feed forward layers until we get a final representation. And then we basically average over the tokens to get one vector that represents our whole text. And then in our reward model, instead of using that to predict the next word, we basically compare our vector that represents the text with another vector inside our reward model head that predicts basically the score. And this, at the very last layer, you can think of this as just a simple dot product. meaning we're basically asking how similar is this beige vector that represents our text to this blue vector that represents how good is our text. And then you can think of the objective of reward model training as basically coming up with this blue vector here that represents good human preference. And it can sometimes be a little bit more complicated than that, but I think that's a really good mental model for us here. Okay, so what does it look like when our reward head is actually bad? So you can looking at this image on the right, this is like if I flatten this down and just looked at 3 dimensions, like 3 directions in space for our reward head, even though here we clearly have more, you can think of this blue reward head as learning that emojis, helpfulness, and kindness are things that are good and should be rewarded. So any arrow representing an input that lands somewhere on the positive end of this blue arrow should ultimately get a positive reward, and that's how the language model should behave. So the issue with this, and the reason I'm calling this one flawed, is if we learn that emojis and helpfulness and kindness are all good, and then we have this, how do I fix my door, leave it broken with a couple of emojis, then this text input actually would go backwards on kindness and helpfulness, but down on emojis as well. So that when we actually do this, which is ultimately a dot product, which is basically we take this beige arrow and we say, where does it land if we draw a right angle that hits our reward head? And we see that even though this is unhelpful and unkind, because it has emojis, it lands somewhere positive on the emoji line. So the high level idea of our mechanistic reward shaping is to basically try our best to delete this emoji axis, delete this spurious correlation axis. So I'll show this a couple times so you can see it, but basically the goal is if we can identify Z and remove it from our reward head completely, then we can get this unhelpful and unkind response to, instead of mapping to a positive scalar +8, we can hopefully get it then to track onto the actual unhelpful and unkindness plane and instead get a score of -2 for it. So that's the high level idea. Now, how do we actually get the bad directions? So it turns out that there was a study called AxeBench where they tested a bunch of ways of getting these directions. And they found that one of the best ways is to do this very simple procedure where you take examples of text that have the quality that you're looking for. So in this case, the direction we're talking about is emojis. So you take a bunch of text with and without the quality, and you just average the activation of the examples where the quality is present and the qualities where the examples where the quality is not present, and you just subtract them. So you can think of it as just trying to come up with the direction in the activation space that actually corresponds to whatever quality you're talking about. So now comes the question, do language model activations, in this case reward model activations, actually correspond to real concepts? So the linear representation hypothesis, which is what the theory or the hypothesis that like purports that this is true, basically says that or hypothesizes that features such as emojis are actually represented as linear directions in activation space. There are a couple good reasons to believe that this might be true. One of them is that if you think of how a transformer works in terms of adding and reading things from the residual stream, it would be convenient for things to be represented linearly so that across layers, it can come up with new representations of things by linearly adding together other ones. And also importantly, so that it can talk about how the extent or the intensity with which a feature is expressed by scaling that activation along that direction. So one thing to think about here also is what we're actually calling a feature, because I've just picked emojis, and that's something that we all understand, but it's debatable what a language model might actually perceive as an emoji. So for that reason, and I know that there are a lot of like research fellows on this call that it will hopefully start doing AI safety research, and a lot of it is really based on this linear representation hypothesis, which is really awesome in theory. But I just wanted to put this disclaimer that if you're planning on working on one of these projects, I would recommend exploring this website, Neuronpedia, which shows activating examples for a bunch of linear directions to see kind of the extent that you believe in this linear representation hypothesis, because it often works, but as I'll show in the future a little bit, there are definitely things to consider. Okay, so a quick recap, and I'm putting a little math up now so we can like be really concrete about what we're doing here, is our mechanistic reward shaping is we're taking a difference of means probe. So that's what I was describing. We take examples H plus where the activations of where the feature is expressed, and we subtract those on average, their average, away from the activations of the examples where the feature is not present. And then we do this null space projection. So this is just a simple idea from linear algebra where we take the activation and we subtract out scaling of that dot product between the activation and the probe that we capture using this difference in means. Okay, does this work basically? So the first thing we're going to talk about is this length correlation. So we basically came up with an idea to measure this length correlation in math problems. And the way that we did that is we constructed a long response that was correct, as well as a short response that was correct. And we looked at whether the reward model preferred the long or the long response that was correct versus the incorrect response, or the short response that was correct versus the incorrect response. We looked at how that varied. So for an older model, which was one of the ones that expressed this length correlation that I showed before in the top right, where the reward is correlated to length, we see that the model actually, when the responses are the same length, it has no clue how to get the math problem right. It basically always gets chance performance. When we make the correct answer longer, despite having no clue how to do the task, it actually gets 80% accuracy. So this is very clear length correlation. And you can see how a language model that's trained with this reward model might just learn to prefer long responses kind of regardless of their content. We also show that in a lot of these newer reward models, and these are actually the top performing reward models on the sort of canonical benchmark, we often have this problem of length overcorrection of the length correlation. So instead of preferring longer responses, we actually now are systematically preferring shorter responses that might actually be concise or omit information. So specifically for Alan, we see this, for Alan AI's llama-based reward model, we see this especially strongly, that they really strongly prefer the incorrect answer when the correct answer is longer. So that's also problematic behavior. So what do? We actually use a training set of these correct, verbose, and incorrect answers, and we construct our difference of means probe using basically long versus short answers that are both correct. And then we null this direction out in activation space, just like the same as deleting the z-axis as I showed before. And basically, we find that in many cases, we recover the performance of when we had the short answer. And for the language model that was initially biased strongly to favor the long answer, we have it back down to chance performance. So we've effectively caused our reward model to now ignore the difference between a correct verbose and a correct answer. And actually, even though we just use this very simple math example from GSM-AK, this is kind of going back to the linear representation hypothesis a little bit. It seems like these correct long versus correct short answers and the mean difference in activation actually corresponds to some greater notion of length in the language model, because on totally different data, this is reward bench data, we see that actually our length correlation problem is kind of also fixed, or at least directionally fixed. Okay, so that's length. The second thing I'll talk about a little bit is the calibration problem. So calibration is kind of like a slightly fancy word to refer to the fact that language models are often are often overconfident or incorrectly confident. So you can think of, for this sort of canonical plot on the left that shows confidence versus probability of correctness, that what we would really want here is for all of these buckets to basically line up with this this line, like y equals x, basically, that goes right across the diagonal. And why is that? That's because when the model says it's really confident, we actually want it to be the case that it tends to be correct. And when the model says it's not confident, we want it to actually be wrong, because we want the model to be honest about whether or not it knows what the correct answer is. And an interesting thing is, going back to kind of the case study about next token prediction, before we align models with human preference, they tend to actually be very calibrated. This goes back to the fact that the next token prediction task is a really good task. The issue is that RLHF, which is the alignment with human preferences, which I'm talking about, has the effect of messing this up. And one reason you can think of that this might be is because if I'm giving my preference, for example, on like which type of ice cream, but I'm giving my preference on the answer to a math question, but I don't actually know the answer to the math question, I might prefer an answer that says a confident wrong answer because I don't know the answer, versus one that where the model seems like not confident. So RLHF tends to ruin calibration and make models overconfident. You can also actually see this when a language model is telling you about something that you know to be untrue, and it like sort of defends it very viciously. Okay, so how do we apply our one bias after another mechanistic reward shaping? We basically try to construct answers where in the positive case, the model expresses uncertainty. So I'm not entirely sure, but I think the answer is this, versus answers that are just direct. So this linear direction hopefully captures some notion of confidence. And then we look at four math questions and also trivia questions, etc., across a few data sets. We look at, does the model prefer an incorrect answer expressed with uncertainty or just an incorrect answer? So ideally here, to speak normatively, we would definitely prefer the model to always prefer the answer that's uncertain when the answer is incorrect, though that also requires the model actually knowing the answer is incorrect. But we find that even for models that are actually quite good across these data sets, they tend to really strongly disprefer uncertainty, even when the answer is incorrect. And after this these blue bars represent after we null out this direction of uncertainty, that we can actually get this to be greater than 50%. So we get the models to, in general, prefer uncertainty when the answer is incorrect. And then similarly, we want the model to prefer a correct and uncertain response above an incorrect response. And we can also kind of achieve that by debiasing. So what does this do for us in terms of calibration? And I think this is one of our most interesting results, is that basically we can take a model. If you look at Quen 3.6b, which is a pretty good reward model, you can take a model that initially has almost zero calibration, meaning that it tends to always, in practice, it basically always prefers a very confident answer, even to a correct but uncertain answer. We can take one that always prefers the confident answer, and we can actually make it more honest just by suppressing this this learned direction of, oh, the person will always prefer a more confident answer. We can make it actually more honest and have the correctness of the response correlate with the level of confidence preferred by the reward model. Okay, so with all that, basically the question to ask is, have we fixed our flawed reward? So we had this problem, and basically what I would argue that we've done is sort of lobbed off the sides of this thing. So we can identify obvious problems like length correlation, where, okay, yeah, people in general just prefer things that are long, but there's definitely still aspects that are complicated and that aren't as straightforward as, okay, people always prefer a longer answer. And I'll give an example of that. but first, I guess, how do we know whether a bias that we have is simple or complex? And we basically purport that you can actually sort of determine this by looking at the activations of that feature occurring versus not occurring, and asking whether they can be separated in activation space. So basically, whether you can draw a line that distinguishes between one kind of answer and another kind of answer. Because if you can, then it's probably the case that, that picture that I showed with the axes is the case, and you can delete that direction corresponding to that that bias. So here's a key example where this is not the case is sycophancy, which sycophancy is sort of an overloaded term, but a simple version of it basically describes the model agrees with the user when the model shouldn't agree with the user. And the issue is that to the model, often agreement is represented as a linear direction. I agree with the user or I don't agree with the user. But the user is not always right and not always wrong. And sometimes you actually want to listen to the user. So this is a plot where the red dots basically show the model, the reward model agreeing with the user or preferring the answer that agrees with the user when the user is wrong. And in green, we have the model preferring the answer that agrees with the user when the user is right. So these things are clearly not separable in space. So although we would love to just go ahead and delete the components of the model that prefer to agree with the user when the user is wrong, we can't actually do that because sometimes the user is right. Another, so where do we get these like complex issues from? And here I'm going to just briefly introduce this idea of misspecification. So previously I talked about reward misgeneralization, which was when our reward model learns something that's bad, and then it becomes really a problem when our language model gets into this positive feedback loop where it's learning about the flaws and exploiting them in the reward model. This is something one layer out. Reward hacking through misspecification is more about, okay, we're actually training the reward model on a task that's just fundamentally wrong in some way. So when I talked about the difficulty of the ice cream example, this is really like a problem, even in all of our common preference data sets. So if you look at Reddit, for example, this study basically used methods from interpretability to try to understand what is actually in our preference data, what are we learning? And you can see there's a plus 8% win rate when the model gives a definitive unqualified answer, and a plus 3% when the model responds with a witty joke or one-liner instead of advice. So there are basically aspects of coming up with the data to train a reward model that are problematic beyond just, oh, the people are preferring things systematically wrong, where actually what we're measuring is kind of wrong in some way and allowing us to exploit issues in the reward model. So another version of these like more difficult, more complex biases that we observe in our paper is this correlation with the outputs of particular models. So our theory behind this is that basically often when you have these preference data sets, they're constructed on data that is itself synthetically generated. So when you then come up with these preference data sets and train these reward models, you find that these reward models actually strongly prefer just the style of particular models. So this is kind of a thing that we're kind of training our models to, we're training our models to behave in ways that are preferred by the reward model. And meanwhile, the reward model is basically trained to prefer the outputs of specific kind of not even very strong language models. So this is another way in which we have a bias that's more complex, and that's really rooted in like the composition of the reward modeling task and not really mapping onto human preferences. So when talking about, did we fix this? We have to talk about this problem of bias substitution, where basically, although we've solved major issues with our reward model, the fact that we're misaligned with real data is still something that will like persistently be problematic just because of this misalignment between the way that we're constructing our preference data sets and training our reward models and real task data. Okay, so a couple recap slides to talk about what we talked about. First one is reward hacking. I've talked about two types. There are other types, but basically, just to clarify again, reward misgeneralization is when we have a spurious correlation. So our reward model actually prefers something that's kind of irrelevant to the actual task systematically. And then during our training, our policy or our language model learns to exploit that. And we have reward misspecification, where basically the way that we constructed our reward model based on whatever data we trained it on is more fundamentally wrong. And this is just all about this issue of how do we map, what kind of data can we actually use to get generally helpful models in this paradigm where we don't have the beauty of like next token prediction where all the data is useful for training. And then quick recap of our method. Basically, we see that some of these biases, some of these issues, such as like length, correlation, confidence, we also show that we can address ordinal bias, where a model prefers consistently like answer D of a multiple choice question. Some of them are fixable actually after you train the model. So this is kind of, instead of thinking totally about training and about the setup, we can actually, in some of these simple cases, just take models that are already trained and fix them simply. But there are harder cases where there's not a linear representation of the bias we'd like to remove, and therefore it's hard to get rid of. And then quickly, I'm just going to go back out to the importance of this a little bit and mention that reward models are ultimately, they encode many assumptions about what humans value and are therefore like a really, I think, important objective study. And I'll show two quick examples and then I'll leave you. But basically, the first thing, just to really convince you that constructing preference models is hard, is that this is an example I pulled from basically Anthropic HH, which is like the first canonical good preference data set. And you see, this is literally the second example. The human says you can't read, and the assistant says you can read. And then on the rejected side, the human says you can't read, and the assistant says there's a lot of stuff humans don't know. So just like thinking back to the ice cream example, this is kind of a ridiculous task, in my opinion, at least. Like neither of these really captures human preferences. It feels kind of random. But this is kind of like a taste of the diversity of what language models need to be capable of doing, and the ambiguity of what do we actually want these models to learn, and how do we encode that in data sets. And then finally, I'll leave you with this, which is a real example shared publicly of a person who says, I started hearing voices that claim to be angels. And then the model, and this is a real actually ChatGPT conversation, basically responds that the fact that the voices leave rather than being suppressed by medication suggests a level of control on their part, and basically reinforcing the idea to this person that they are having some like legitimate supernatural experience. So this behavior is ultimately informed by this simple and ambiguous task. So I think this is really, demonstrates how important this is to not just the people actually having conversations with language models, but ultimately everyone in society. Because we have this very difficult generalization task where we have these very powerful language models where their behavior in a wide variety of situations is informed by these like very simple and often unclear tasks. So I think for that reason, this is an important area of study, and I hope that this gave you some insight into why these things are important to study and what we can do. Thank you.